Welcome to angular and linear velocity. You've just finished learning about different parts of circles and about central angles and inscribed angles. This lesson will continue along that path in that you will examine central angles and the rotation of those, as well as the distance that a circular object may travel. Our objectives are to understand the relationship between angular and linear velocity in circular motion, as well as to analyze relationships of angular and linear velocity in systems of pulleys and sprockets connected by belts. When you are looking at angular and linear velocity, you're looking at things such as how many times does this wheel on this motorcycle rotate? That would be angular velocity. You're also looking at how far do you move with each rotation, and that is basically your linear velocity. We'll look at that in a little more depth. Let's first look at angular velocity. When we say that a record is rotating at 33 1/3 revolutions per minute, RPM, we are giving its angular speed. We are telling how far it rotates in a given amount of time, or how many times it rotates in a given amount of time. Here's an example. This is a merry-go-round. And on here, there's a girl that says, "How fast can you spin me?" And then the other girl or boy says, "I think I'm 6." So how fast is this going? Well, this is actually what we're interested more in is then how many revolutions per minute. The faster it's going, the more revolutions it's going to travel per minute. So that cartoon relates to our angular velocity. Notice one more symbol up here. This little W is an omega. And that's often how we represent angular velocity. Now let's look at velocity when we have two circular objects together, meaning they're rotating together by a belt. The one thing you have to understand, and I would write this on your notes to help you to think about it, is that the ratio of angular velocities for two linked pulleys or sprockets is the reciprocal of the ratio of the sizes. Reciprocal means that they're flip-flop. So, in other words, if this big one had 40 teeth and this small one had 25 teeth, that's 50 to 25, or in other words, 2 to 1. So we could write this as 2 to 1, or even as a ratio, 2 to 1. This has a lot more sprockets. But when we're talking about the velocities, think about which one's going to move faster. Let's look at that. Here's an example of two gears that are spinning together. If you can picture their teeth are connected, look at how they're spinning. Imagine the number of gears on this big one. We said, say 50. Now imagine the number of gears on the small one. We said 25. There's less gears on the small one, right? We simplified this to 2 to 1. The blue one has twice as many as the purple one. But which one's spinning faster? Watch this a minute until you can see that the blue one is spinning slower and the purple one is spinning faster. Notice that the purple one takes 2 rotations for every 1 rotation of the blue one. And that's what we mean by reciprocal. So while the blue gear has twice as many gears on it, or the blue sprocket, the blue gear is spinning at half the pace of the purple, or the purple one is spinning at twice the pace of the blue. So, as we said, in general, the larger pulley here rotates slower than the smaller one by the reciprocal of the ratio of the sizes. Let's try an example. Let's picture a bicycle. So here on the front, where the pedal is connected, it's directly connected to this big gear. And on the back, this is where the tire is connected, or the wheel is connected to the back gear. Now in this example, we say that the mountain bike set is set up so that the pedal sprocket, this front one, has 42 teeth. So we'll go ahead and write 42 here. And the rear wheel sprocket has 14 teeth of the same size. So consider this and let's answer these questions. We'll go ahead and write 14 and 42 here to help us think about that. We're considering the given teeth per sprocket information that's given. Try to answer this question. What does this information tell you about the circumferences of the two sprockets? Pause the video and see if you can answer this question. All right, if you set this up, we know that we have a ratio of 14 to 42. Or we could write it as 14 over 42, which reduces to 1/3, or 1 to 3. In other words, this bigger sprocket 3 times larger than the smaller. So the circumference of the bigger sprocket is 3 times bigger. Now, B, suppose that the rider is pedaling at an angular velocity of 80 revolutions per minute. Think about what this means. You're pedaling at 80 revolutions per minute. Here's your pedal. It's directly connected to the front sprocket. So, what is the angular velocity of this pedal sprocket, as well as what is it for the rear sprocket, which is connected to our wheel? Pause the video and see if you can come up with an answer based on your understanding of angular velocity and how these two sprockets relate to each other as far as circumference and the ratio. For the first part of the question, what is the angular velocity of the pedal sprocket? Well, that's actually given. It says that we're pedaling at 80 revolutions per minute. So we know that's 80 revolutions per 1 minute. Our second part, what is the angular velocity of the rear sprocket? That's where we have to think about our ratios, 1 to 3. Remember, the small one actually rotates 3 times faster than the big one. So if our angular velocity of the big one is 80 revolutions per minute, we need to take revolutions and multiply it by 3 to get 240 revolutions per minute. And that is the angular velocity of our rear sprocket. Let's now explore some linear velocity. Linear velocity says this. If P is a point on a circle, we'll assume this blue dot right here is point P. I'll green so you can see it better. P is a point on a circle of radius r and moves a distance s. Started here and moved to here. Moved a distance s on the circumference of the circle in an amount of time t, then the linear velocity, v, we'll call it, of P, this point formula, where velocity is equal to the distance that it moved, which we call s, divided by t. This formula is actually derived from the distance formula, where we have distance equals rate times time. If we consider our velocity to rate, let's solve for r. To solve for r, we would divide by t. These would cancel, and we'd say that rate is equal to our distance over time. These two are the same formulas, we just use different variables to represent things. Rate is represented by v for velocity, and our distance is represented by s for the distance. And in a circle, we look at this arc distance as s. Let's look at an example. A point on a circle travels 5 centimeters in 2 seconds. Find the linear velocity of the point. Well, we're looking for the distance, so our linear velocity is equal to 5 centimeters divided by 2 seconds. Distance divided by time. And that equals 1.5 centimeters per second. And it's really as simple as that. In other words, if this was a wheel rolling down the road, it would travel at 1.5 centimeters every second. Let's take this understanding and apply it to our bike example from earlier. How far does the bike complete revolution of the 14-tooth rear sprocket? And another thing to know, that the bike does have a radius of 33 meters. That's important to know. We need to know how far it travels, so we need to know the circumferences, and the radius help us find the circumference. Pause the video and see if you can answer these questions, and then we'll go through them. For this first example, sometimes it helps to draw a picture and really think about what's happening. This rear sprocket is directly connected to the wheel, so that, remember, if we have one complete rotation of this rear sprocket, well, then the wheel has one complete rotation. So this radius of 33 centimeters is important. So what we're looking for is, what is the distance one time a wheel? So as this wheel travels path, we are going to be covering circumference one time. Well, remember that the equation for the circumference circle is equal to pi d, or 2 pi r. In this case, our radius is 33, so we would have 2 times pi times 33, or 66 pi, and if we multiply 66 times pi, we'll do 66 times 3.14, we get it of 207.24 meters. So with one rotation of this rear sprocket, that bike moves 207 centimeters approximately. Now we could always convert that to inches or feet to make it more understandable, but that's how we determine how far the bike travels. Now, how far does the bike travel for each rotation of the front pedal sprocket? Well, remember that every time we rotate once around the back or the front pedal sprocket, the back one rotates 3 times. Therefore, for every one complete rotation of this front pedal sprocket, the back wheel will rotate times. Well, we know that one rotation is the same as 7.24 centimeters, or 66 pi. Multiply that by 3, we'll answer to this question. So, times 3, we get 621.82 centimeters. How far the bike will travel for each rotation of the front pedal sprocket. Let's look at C. If the rider pedals at an angular velocity 80 revolutions per minute, how far will she travel in 1 minute? In this last case, we know that one rotation is 622 centimeters, but if she is traveling 80 revolutions, we could multiply that by 80 per minute to see how far to travel. So if she travels 600 centimeters for one revolution, does 80, then we can just multiply that by 80 to determine that her distance is 9,737.6 centimeters per minute. So taking what you know and applying it to each of these problems can help you to solve them, as long as you understand the difference between angular and linear velocity. Remember that angular velocity is how many revolutions you're going to make per minute or per second or per hour, versus linear velocity is what is the distance you're going to travel per minute or per second or hour. That concludes our lesson today on angular and linear velocity. So now you should understand that relationship between the two, and then be able to analyze different relationships with sprockets or pulleys, or even be able to solve problems using angular and linear velocity.